Yeah, so this talk is titled Armchair Type Theory. Who could spot the type error in this opening slide? No, you'll notice there's a couch there when it's supposed to be an armchair. So, yeah. My name is Zach, Z on Twitter. I'm actually from Florida. So, yeah, from right there. So if you want to know anything about the state, feel free to check out this website, Google, and I can help you out with that. But, so this is JSConf, and JavaScript doesn't have types, but let me motivate you a little bit. This was a bad year for software engineering. There was the go-to fail, and then there's also something called Heartbleed with a really nice logo. And I think it's becoming clear that we're good at building features, but maybe not so good at exercising all of the unhappy paths. So we're really good at building features, or exercising the happy paths, and usually what's out of sight is out of mind, and we don't notice when we're exposing all of these opportunities for failure. So given that we're horrible at exercising these unhappy paths, code reviewers, QA, the open source community even missed these bugs that were in the software. We have to rely more on computers, our computer friends, who are relentlessly unforgiving, and which is a good quality to have when you're reviewing software. So this talk is titled Armchair Type Theory, so of course we're going to be talking about type theory. And you can kind of see in the background there, that's Bertrand Russell. He invented type theory to basically solve a bug in formal logic. So in programming languages, we use type theory to develop type systems. And you can, if you're not familiar with type systems, you can basically think of it as like JS hint on steroids. So it'll actually, it's actually part of the language. Usually languages that have type systems, they embed it in the language, but it's also a static analysis tool. So, and nothing short of running the actual program will guarantee it's correct, but type systems provide a way to narrow the scope of what's a valid program, sort of the same way that your parser will narrow the scope based on the grammar of the language. The system will narrow it further using extra information, context about what the program means, and this is something you only do with a type system. But of course, there'll be trade-offs. So if you're trying to do something dangerous, or anything with safeties built in is going to make it harder for you to do like certain things, but that's part of the trade-offs you have to make. And I'll talk about that more when we get into things that are relevant to JavaScript, like PureScript and TypeScript. Because of course, JavaScript itself doesn't have static types. It does have these cool number types like Brian mentioned, but nothing resembling static typing, unless you count ASM.js, which is sort of like a clever reuse of operators to act as like a static typing hint for engines that understand it, at least. But it's not really relevant to JavaScript in general. So we have these new languages that have been developed that compile to JavaScript, and these ones especially target JavaScript as their backend. So TypeScript, of course, has been around for a while. I'm sure most of you are familiar with it. And then there's also something called PureScript, which is newer, and it resembles Haskell. And also Elm is a really cool language that it's also similar to Haskell in certain ways, but it's targeting FRP, so functional reactive programming. I highly recommend it if you're trying to get into functional reactive programming and you also want an additional challenge, because who doesn't want that, of learning a purely functional language. So, but we're going to focus on TypeScript and PureScript. And I'm not going to get into actual type theory. Sorry for you, those of you who came to this 9:30 talk at JSConf to actually learn about this stuff, but we can sort of form it using this metaphor instead. Basically what the type system is doing for most type systems that we use in popular programming languages that have them, they basically look at the value, the shape of the value at different parts of the program where it's passing through like functions, function application, operators. Whenever you're passing that value around to these applications of a function or operator, it'll check the value and make sure it forms the shape. So these blocks are representing the values, and then the holes in this block here are the API boundaries where that value is being passed around. And here's an example of TypeScript where you'll see this is like a function, but it also has typing annotations for the first name and last name, expecting them to be string, and then also it'll return a string. And you can imagine this as, one way to imagine this is if there was assertions like generated or inserted into your program to make sure that it was always the correct value, the shape of the value was correct. But the advantage of this, as opposed to like unit testing or using assertions, is that you're guaranteed to have, based on the types of, you're guaranteed to have 100% code coverage if you're using like something like Haskell or PureScript. It's guaranteed to be 100% coverage because the program has to be typed. But it's also done statically, so you don't have to actually make sure you have 100% code coverage, and you don't have to actually run the program. So you'll be able to catch errors faster as you know, it's type system. Another way to look at it is the compiler is sort of running a simpler, dumber version of your program at compile time. The type checker is reading the AST, taking the types, and sort of running computations on the types themselves to make sure that that passes. And then once you do that, it's like you have formally you have like a proof of your program. So we want programs that can prove themselves. Sorry for this next. We want programs that can prove themselves, sort of like Daniel the Karate Kid proved himself. And you'll want to be able to sweep the leg, so to say, on certain classes of bugs. But depending on the type system, you'll be able to eliminate those bugs from your programs, basically. So, sorry, no more of these Karate Kid references, I'm sorry. But, yeah. So of course, there are going to be trade-offs, especially the different type systems. You might notice that C#, Java, and Haskell have like completely different looking field. The field of the type system is different. And that's also the case with TypeScript and PureScript. It's basically like a Java, C# versus Haskell, classical OOP versus purely functional. But what's interesting about TypeScript is, of course, it's a superset of JavaScript. So you can take a standard JavaScript program and sort of incrementally add types to it if you want. So you can take a standard function and then add types to it. And this is, you can do this for parts of your program at a time. And of course, it has the basic things you would expect from a type system that is like C# or Java. But I wanted to highlight a special part of the type system, and that's the any type, which it does exactly what you would expect. It basically lets you substitute any value for that variable that's annotated with the any type. And you might wonder why, you're you can just use an untyped language, but you're having like an untyped JavaScript, that you add typed JavaScript to it, and then you interact with an untyped subset of the JavaScript. And it's sort of like that. I don't know if you've seen this before. The island in the Philippines, it's called Luzon Island. And then there's if you zoom in on the southern end of it, there's a lake. And then if you zoom in on the lake, you'll see that there's another island. And then on the island, there's another lake. So, you have this sort of untyped environment where you add types to it, but then you can also interact with other untyped, maybe foreign libraries that you need to interact with. And also, if anyone's keeping score, dynamic typing is a subset of static typing. So static typing is actually more general than dynamic typing. You basically punch a hole in the type system and add untyped, like this any type to it. And so dynamic typing is basically having one type, and then other static typing is when you add additional types besides the any type. So you might be wondering, again, like why use a typed language when there's so much more flexibility with the untyped language. And really the type systems are adding all of these extra features so that you can have these expressive programs that you can approach the expressiveness of an untyped language, but still have the guarantees that those classes of bugs are absent, which is, of course, the main reason why we want to have these the type systems in the first place. And PureScript, I'm going to talk about next, has a completely different approach than TypeScript. So TypeScript was trying to achieve the improbable task of adding a sane type system on top of JavaScript and keeping the same JavaScript semantics. So PureScript took a completely opposite approach, like scrap JavaScript as it is and add a language that resembles Haskell, so it's purely functional. You'll see the syntax looks basically like Haskell. And if you've never seen it before, it looks like completely foreign. You might not know how it works. But that might be a good thing because it'll sort of set you off guard, put you on your toes, because the language itself functions a lot differently than standard JavaScript or object-oriented programming. So you could say it's sort of like JavaScript, the functional parts. It takes the functional parts of JavaScript, but also wraps it with a really nice type system to give you those assurances that you need. And one property of the type systems that I want to highlight, the difference between TypeScript and PureScript, is something called SOUNDNESS. And SOUNDNESS basically means that every program that you can express in the language, in the type system, if it passes the type checker, then it'll be a valid program, and it'll be valid at runtime. And a lot of research goes into assuring that this holds. So whenever there's like a new type system developed that has different guarantees that it'll provide, they go through great lengths to assure that it's still sound, because soundness means that at runtime those guarantees that it's supposed to make will hold. But for TypeScript, it's a different story. A guy named Toivo pulled out a theorem prover and went through TypeScript's language spec and showed that a part of the rules were unsound. So there were expressions you can express in TypeScript that will pass the type checker, but if you run them at runtime, you'll get like a type error because it's not actually a valid expression. And they have actually notices in their documentation on, why they have certain unsound expressions in their language. And so the bug was this issue was of course, it was marked a won't fix. And this is my favorite won't fix GIF. I encourage you to post it on GitHub issues. Whenever you have a won't fix, just Let's just watch it a few more times. So good. So yeah, so they basically said, in order to keep the type system more lightweight, they didn't want to add these rules that would guarantee soundness, but perhaps make it less intuitive for people trying to build JavaScript programs, because we're used to a certain way that the language works, being able to pass certain values to functions, and adding soundness might make that less intuitive for most JavaScript programmers, so it was a trade-off that they had to make. So like the hardcore type theorists might get angry, but in the end, it might be a net gain for the rest of the users. But this is not so easy of a trade-off for languages where memory safety is a concern. So in JavaScript, you don't have that control to, say, like dig into memory and alter things. But for languages like C and C++, an unsound type system would lead to things like heartbleed, for example. And with great control comes great responsibility. And this is, of course, where I would mention a language like Rust, which Nico here gave an excellent presentation, and then the video is available online, where he goes through the ways that Rust will guarantee memory safety. And it's not only the shape of the values in Rust's case, because there's like concurrent processes happening in different ways to dig into the memory. So the type system will actually give you types that you can annotate variables with that will track like ownership, and different things that will help you protect against like a mutation of shared data. So with something like Rust, you wouldn't be vulnerable to these classes of memory vulnerabilities where you can basically violate memory safety. So type safety is an important aspect, and soundness is also an important aspect when you want to guarantee memory safety. And a part of how Rust does that is, like I said, it makes everything explicit. So explicit annotations on variables when you need mutation, and a lot of that you can do in C and C++. And there is some slowdown when you basically do things the right way. But the benefit of making things explicit is you'll save the headaches later on, and you'll eliminate these classes of bugs. So being explicit really is worth the trade-off, I would say, because you're going to get that performance penalty if you use language like C and C++ and you do it the right way anyway. So something like Rust at least has a coherent sound type system that would guarantee that those memory safety bugs won't creep up, because C and C++ have tools to prevent that, but they're sort of added on later, and it's not a coherent sound type system. So I would say being explicit is the key here for Rust. And in general, my tips would be let's use the computers for what they do best. Like perhaps we're not best suited for digging into these really, like, the unhappy paths sort of grow exponentially because there's so many unknowns that we don't see, and it's hard for us to see them. So if we have like a system that is enforced by the computer, like a strong type system that we know is sound and won't allow us to sort of create these errors that we're sort of incapable of perceiving ourselves, then we should do that. We should use computers as much as possible for those tasks, because otherwise, we've seen what happens. And also, more explicitness now, though it might be more complexity up front for you. If you're more explicit, then you'll save your sanity later on when unexpected things happen.